Warm welcome from my side. Thanks for having the opportunity to present today my latest iteration of my PhD studies, which are dealing with engineering situation-aware dynamic risk assessment monitors for autonomous vehicles. And the goal of this approach is basically to slightly lift operational performance of autonomous vehicles, but without deteriorating safety. So what is about to come in the next minutes? So first of all, I'm going to motivate why we need dynamic risk assessment and in an autonomous shuttle use case. Then I'm going to rest some focus on comparing existing DRA approaches in common AV architectures and trying to kind of discuss why this is a little bit problematic from a safety assurance point of view. And as an alternative solution, I'm going to present the core ideas of situation-aware dynamic risk assessment. And I'm going to highlight the risk decomposition concept that it uses in order to perform a qualitative runtime risk assessment. And last but not least, I'm going to talk about safety argumentation concerns that naturally pop up when we are building a dynamic risk assessment monitor that is part of the safety function. So what you are seeing on this slide on the right side is actually an autonomous shuttle bus that has been built up at the Technical University of Kaiserslautern. And basically the use case is to operate in pedestrian zones like university campus or like city center zones where we have quite crowded situation with respect to pedestrians walking around where the autonomous shuttle actually is driving. And one issue that has been found often in these highly interactive environments is that robots are actually freezing without having an initial idea of why this is the case. And this means that if we have, for instance, pedestrian streams that are kind of walking by the autonomous vehicle shuttle, it simply stops and does not move. And one potential cause for this not moving is actually that the risk assessment that the autonomous vehicle is carrying out with respect to continuing driving at a particular speed is actually too conservative, because internally it somehow tries to get an idea whether the pedestrians will actually move themselves in a dangerous situations or actually will cross the path of the AV. And the effect is that we have false positive safety interventions, so meaning like the vehicle stops because it believes that the pedestrians are at risk, although they are, from a human perspective, just like walking along the autonomous vehicle. And this is a problem. So, and this talk is actually looking at the questions of what is this issue and how does it emerge when we are looking at current DRA approaches, and what might be an alternative that is assurable but is also capable at the same time to improve the driving performance away from using worst case assumptions but without deteriorating the safety. And before digging deeper into the answer of these questions, let's understand a little bit more the general idea behind AV safety engineering processes and dynamic risk assessment. So if we are looking at a common nominal driving agent, then the basic sense plan structure is actually composed out of a perception stack that is populating a world model with relevant information, and a motion planner is basically generating ego trajectory candidates to be followed. And these trajectories are then executed and form, then basically the externally visible AV behavior. And if we look at that from a safety perspective, then basically an accident can occur if somehow a hazard is actually occurring with respect to an AV behavior. But it is important to note here that the hazard is just a potential source of harm. So any AV behavior in principle can lead to an accident. And so that this can happen, actually the right operational situation needs to be present, and external risk control measures need to fail, and only then we will have an accident. So what we are typically doing when we're doing safety engineering is that we are trying to get an idea about the potential hazards of our system. And then we are trying to assess the risk of this hazard in a particular operational situation with respect to a particular accident that we would like to rate the risk of. And to do that, a common approach that, for instance, is also performed as part of the ISO 26262 is to look at the operational situation likelihood, also called exposure parameter, rating the controllability of external actors. For instance, in our autonomous shuttle use case, this would be like the controllability of pedestrians around to remove themselves from dangerous situations, and the severity parameter actually deals with the consequences of an accident that happens. So when we have performed this risk classification, then we usually get an idea about try to get an idea about potential causes of the critical hazardous events. And there are manifold cause types that can lead to these AV behaviors that might be risky. So one that is commonly known is actually the functional safety causes, where we're dealing with software faults and hardware failures. But recently, actually, the SOTIF standard also is addressing sensor performance limitations and unsafe behavior specifications that may lead to hazards without having software faults and hardware failures. And one particular fourth class is actually that the nominal driving agent just uses wrong assumptions about the current operational environment. For instance, that the behaviors of external pedestrians here are wrongly predicted in a critical way, which also then leads to behaviors that might be dangerous. So if we are only doing the risk assessment at design time, then the consequence is that we are posing our safety goals that address these hazardous events with a particular integrity that is based on the worst case risk. So therefore, we can always assure that it is safe, but the consequence is that we are actually operating much more conservative in low risk situations than would be necessary. And the consequence is that we have to build a safety concept that is actually adhering to the safety goal, and this safety concept is then allocated to some design elements, and the safety is then demonstrated via verification and validation. So this is actually how this looks like in general when we are performing design time safety engineering. But since we've heard that there's a drawback when we are building our safety concept based on worst case risk, one way to improve the situation is to use dynamic techniques, so meaning like shifting parts of the risk assessment to the runtime, which effectively means that the functionality of relating risk-relevant situation features, so detecting them dynamically and reasoning about the current level of risk in the current situation, can give us some potential for improvement. Namely, if low-risk situations actually are present, then we don't have to act overly cautious. And if we move this risk assessment task into a runtime component, then clearly the DRA monitor is also a part of the safety critical function, and therefore all proper safety engineering and validation and verification demands, they also apply for such a DRA monitor. And this means that we have to make sure that the underestimation of a risk of a particular hazardous event is always avoided. So kind of put differently, the DRA monitor, we need to demonstrate for it that it avoids that unsafe ego trajectories are actually being classified as safe. That's the critical failure mode of this safety function. And although it is often not explicitly called like that, many current AV architectures, they perform dynamic risk assessment in one or the other way. And that's why we should now review the state of the practice DRA approaches, also from a safety perspective. So the most straightforward technique for making sure that the trajectories that are generated by a motion planner and a nominal driving agent are safe is to use so-called trajectory verification. And it seems natural that if the motion planner outputs a trajectory, that we also perform the risk assessment on a trajectory level. So this means an ego trajectory candidate that is coming out of the motion planner is actually compared as part of a risk metric with the trajectories that are predicted for other actors in the vicinity. And if this risk metric actually exceeds a certain threshold for criticality, then we decide whether we have to perform, for instance, a minimum risk maneuver, or whether we can select or execute the trajectory with an acceptable risk. So important here is that we have the actor trajectory prediction involved here. One example where we, on the first glance, might not think that this is a trajectory verification is the so-called responsibility-sensitive safety model. So there are some equations which define on the kinematic level minimum distance criteria, which are effectively a binary risk criterion. And although this is not explicitly mentioned in the equations, the underlying motion model behind those equations assumes that the front vehicle brakes with maximum deceleration. And by using kinematic equations, we can implicitly pose the trajectory prediction in a closed form solution, but it is still a trajectory that is assumed to be present for the front vehicle. And the same holds true for the ego vehicle. So here we are seeing already that worst case assumptions are involved. And in RSS then basically the proper response reacts to a violation of the minimal distance criteria. So this means like the binary risk criterion is acted upon with the proper response to go into the safe state basically. So the third approach class that we have is not like taking an ego trajectory candidate of the motion planner and assessing whether this is safe, but it is a little bit more complex but follows the same principle. Here we want to generate safe behaviors or safe trajectories from the ground up. So this means like we still have to predict the trajectories of other actors, but now we don't take an ego trajectory candidate, but we take the space of all possible ego trajectories, and by using a risk and performance metric as optimization criteria, we try to find in this ego trajectory space the one that is safest and performance, so to say. And notably here, also here, this approach is highly dependent on having an actor trajectory prediction that is accurate enough. Plus, the second key assurance challenge here is always that apart from the prediction that needs to be accurate, also the perceived features that are relevant for this prediction, they also need to be perceived reliably and determined reliably. And for all these approaches, so since they also perform some way of dynamic risk assessment, it would be necessary to somehow provide a meaningful argument why actually it is avoided that unsafe ego trajectories are being classified as safe. And so we see that existing approaches rely on this actor trajectory prediction, a risk metric that defines scale and criteria on pairwise trajectories. So we may ask ourselves, why is an argument now hard of avoiding safety goal violations with these approaches? Yes, and to answer that questions, let's look a little bit more into detail on how these trajectory-based DRA methods work. So on the left side, we are seeing basically two vehicles where the red one is the ego and the blue one is another actor that we would like to predict the trajectory of. And the trajectories are positions or poses over time. And on the right side, we are seeing the start situation at time t0, where we are having, let's say, a variation with respect to the other vehicles' starting positions. This might be at the t0, basically due to measurement uncertainty that we have different starting positions here. And for the ego one, we assume that it is known what is there. So now what we are doing is we are predicting via the use of an actor motion model this current pose of both the ego vehicle and our other vehicle into the future. And in order to do that, the actor motion model contains a lot of assumptions where it is determined what the probability is, like indicated here on the right side with P1 and P2, on how a particular starting position may end up in different trajectories at a future point in time. So what is then usually done is that kinematically impossible trajectories are actually removed from the space of possibilities. So this means like on the second plane on the right side, we are having actually like each point is representing a particular trajectory of possibility. So in the next step, we are using a risk metric that needs to solely define based on these pairwise trajectories, whether a collision can happen. That is easy because a collision is represented by a trajectory overlap, or in the probabilistic case, via a distribution overlap of these trajectories. And if it is like near a collision, then we can pose also that we may have high risk between a certain pairs of trajectories, if no collision happened, but it is a near miss. And the issue is that actually all the assumptions that are from a human perspective understandable when we say this is a risky situation. This is basically situation features that influence the behavior likelihood of a particular actor, that influence the controllability, and also to a certain extent the severity. They are all hidden in the actor motion model. So the critical point is actually that the probabilities of coming from the start scene to the trajectory is basically not traceable anymore to the final risk assessment. So if we see that a risk assessment was high or medium or low, we don't know why this was the case in the first place, because it is hidden in those probabilities and in the actor motion model. And humans, on the other hand, intuitively do not assess the risk based on an internal trajectory prediction. Instead, what they do is that they directly relate situation features to risk without this detour over trajectories. So for instance, if I'm seeing a pedestrian walking over the street with headphones, then what I do is I reason about the low controllability due to the absence of situational awareness, instead of constructing a trajectory around this pedestrian or a trajectory space that is reflecting this low controllability, and then defining the risk based on in the trajectory space. That's not how humans work. They are more on a qualitative level. And with this idea in mind, let's see how maybe an alternative solution can look like that reflects these aspects. So here we are seeing again, the state of the practice approach essence with the behavior intents, the projected trajectories, and the respective risk metric that is defined based on pairwise trajectories. And as indicated in red and explained on the last slide, the trajectory level, so going down to the trajectory level, breaks this traceability from risk-relevant situation features on the one hand to an understandable risk estimate on the other hand. And the situation-aware dynamic risk assessment approach that I've been developing as part of my doctoral studies actually tries to overcome this problem by building a qualitative risk model, and that decomposes risk based on the commonly known qualitative risk parameters. So exposure, controllability, and severity. And for each of these risk parameters, cause-effect models are built that actually directly relate the risk-relevant situation features to the respective contribution in the risk metric. And the benefit of that is that by having this traceability explicit, we can also then execute parameter-specific risk control actions. So this means if we find that the controllability of a particular pedestrian is impaired due to wearing headphones or something like this, then we know that we can potentially do something about it to increase the controllability by, for instance, trying to communicate basically with this pedestrian in a way that he is actually kind of turning his head around or something like this. Yeah? So this example was quite specific, but the point is that if we have this direct relationship between a situation feature and the risk, we can also try to modify the situation feature directly. And this is a way on how we can control or modify also the risk. Okay, so now having this on the high level, how does the decomposition look like in more detail based on an example? So here on the left side, we are seeing basically the view from the autonomous shuttle that is driving over the university campus. Unfortunately, this was due to COVID, and we weren't able to kind of capture scenes with crowded pedestrians, but the concept can be explained equally well here. So on the right side, we are seeing that we would like to decompose the risk of a pedestrian collision when continuing with the current speed. And if we are looking at the situation exposure, then this is slightly reinterpreted with respect to or compared to the notion of situation exposure in the ISO 26262, for instance. So I interpret the situation exposure basically as having macroscopic risk influencing situation features. So asking ourselves, if we wouldn't know anything about the detailed situation that we see on the left side, so whether there is a person or not, what information that is more macroscopic nature could we use in order to get an idea about prior risk. And one such feature could be that, or the concept could be that we try to get an idea about the general expected pedestrian presence on the campus. So this could be, for instance, knowledge we can use about the university lecture times, where we know that in the breaks, especially many pedestrians will be on the campus. And this can be actually detected by just having a look at the time of the day. So independent of our local sensor techniques, we can still get an idea about the macroscopic risk here to a certain extent. But this is obviously not sufficient. And if we detect a particular person, like the right person here that is kind of playing on his mobile phone or looking on his mobile phone and not looking at the AV, that's the important thing, then we can try to reason about the controllability of this particular actor. And how can we do that? Well, we build a model of how actually pedestrians perform decisions when they go around. And the hypothesis is that a person that is aware of an AV and can localize the AV and can, to a certain extent, predict what the AV will do, will plan and execute its own behavior or its own behavior in a safe way, because no one actually deliberately jumps and wants to hurt himself. And last but not least, it could also be that this behavior is indicated to the AV, and therefore we get an idea what is going to happen next. So if we kind of further decompose this, then what we are looking for is impairments of these capabilities. So for the attention, so the first one, so the attention capability is impaired, for instance, if we have audiovisual distraction. So cell phone usage is an indicator variable that can indicate whether this distraction is likely or not. And the consequence is, if we find that the attention is impaired to a high degree, then what we conclude from that with respect to the controllability is that actually the localization will most likely not happen due to the attention, and that all further steps in the cognitive behavior chain, that they will also most likely fail, indicating low controllability. And the same holds true for the decomposition of the other capabilities shown in green here. So another example would be that we say the localization capability is impaired, for instance, if the perception area limit of this or the perception area of the person is limited. For instance, if the pedestrian view direction is in a different direction than where the AV is coming from, basically. So then we would conclude, okay, the localization capability is impaired. And one concrete situation feature which we can use to as a surrogate to predict that is the eye gaze direction. And the last example would be like on the indication side of things. That's also quite intuitive, that the explicit right-of-way communication of a pedestrian can also be used to get an idea whether he will now go in front of the vehicle or not. So one feature that we could detect in order to get an idea of that is the hand gesture. So there are these usual hand gesture of friendly people who actually let then the AV vehicle pass. So having this general risk decomposition concept, important trait here is that we have these white boxes in between. So often there also exist risk models that are purely based on, let's say, statistical relationships between, let's say, the outputs of the model and the yellow boxes, the inputs. But the white boxes, they somehow present the reasoning strategy of why actually a particular yellow situation feature is relevant for a particular risk parameter. And this means that we can lay out and somehow make it understandable for humans on why a particular feature state has an influence on which risk parameter. Oh, sorry. Okay, so having now understood the concept, so this is a model that actually is the full model for the pedestrian collision risk model for the autonomous shuttle that we've developed as part of a research project. And yeah, we achieved that with a combination of analyzing traffic behavior research on feature risk influences. So there has been already quite some controlled experiments to do that. And yeah, this is combined and used in a much more refined hazard identification and risk assessment analysis that is comparable to the ISO 26261. But the difference is that the situation model used for decomposing the situation space is much more detailed in this case. So I will now go, due to time reasons, more quickly over this slide. So kind of this resembles what I've just said, that actually this kind of risk decomposition model enables to somehow also in a textual representation kind of understand the steps in reasoning of which assumptions we use in order to post the situation feature influence to the high level risk parameter. So this means, for instance, so if the absence of a cell phone usage is reliably detected, this is important, then we can assume that the cognitive attention is there. And from that, we conclude that the capability to localize CLV is assumed to be not impaired upfront. And the same holds true for the other path and all paths in this model. So if we have this model, then we don't have yet a component or a software component that is actually using this model to do something at runtime. So we need to build an actual, let's say, safety mechanism or a software component. And this is the situation-aware dynamic risk monitor. So in here we see just in the middle the respective risk decomposition model that we have built up and engineered. And I won't go into detail in this talk on that, but what we are doing in the next step is that we are formalizing these relationships, which are conditional and probabilistic. So not every time that an eye gaze direction is in the direction of the AV, this also means consequentially that the AV is properly localized. So this is conditionally and probabilistic. And we are transforming this qualitative causal model here in the Bayesian network. And if we are at runtime, then we also need consequentially a component that is performing the perception of our situation features so that it can be fed into the Bayesian network for performing a runtime inference. And on the right side, we are seeing that the outcome of this risk inference is used by a component to plan on how we can control or modify the risk in case it is too high, or what we can do in order to relax our behavior and still drive, even though we have had a freezing robot stop, for instance. And as I said in the beginning, since we have a safety function here that determines the risk, and consequentially risk underestimation is safety critical, we need to treat it as a normal safety function. Therefore, safety engineering is relevant. So this means we need to think about what are concerns that may lead to the fact that actually we will have a risk underestimation. And one such concern, obviously, is if the perception is impaired, so that we critically misclassify the perception. And this means in the concrete case that the eye contact is detected, but in fact it does not exist. And this would mean that we kind of plan, because we assume eye contact is there, risk is lower, we assume that we can drive, and if we have a misperception here, then this is problematic. However, this concern, since only the commission failure here is relevant, we can use a false positive detection as a safety concept to assure that this does not happen. And this even means that we can use in certain cases machine learning, for instance, for the eye gaze detection, because we have this false positive detection. And machine learning algorithm in general has a hard time to be verified if we or to be validated if we have to detect, basically with traditional algorithms, the eye contact in an image that we don't know of. But here the point is that the ML algorithm would provide a detection that we just need to verify, and this is possible with traditional algorithms. So the second concern is actually that the conditional assumptions in our Bayesian network do not reflect the reality properly, and due to the modular structure of the risk decomposition model, we can validate these conditional assumptions and parameterize the probabilities with dedicated controlled experiments in a modular way. And afterwards, after we have learned the Bayesian network, we can perform expert-based verification, for instance, with sensitivity analysis. But since we know all the internal intermediate concepts, we can do this in a stepwise way. And the last concern that I would like to highlight today is the risk control action has no effect. And this is actually addressed by that we are only doing small interventions for this risk control or modification of feature situation states. And we monitor whether the intended effect is actually has emerged. Yeah? So this means, like, if a pedestrian is going with his back pointing to us, and we are kind of putting on the horn or something like this, we, before starting to drive, what we are doing is we are kind of monitoring whether it actually turns around, and we assume that this intervention actually reduce the risk, because now he will be then aware and attentive of the AV and consequentially plan safe behavior. So coming to the end, basically a summary would be dynamic risk assessment is clearly part of the safety function, and therefore respective safety engineering techniques are relevant. We have seen that the absence of safety goal evaluation is hard to demonstrate for trajectory-based TIA approaches, because going on a trajectory level actually provides a gap with respect to the traceability from situation features to the risk estimate. And the SINADRA approach addresses this challenge by going more on a qualitative level, similar like humans actually judge risk influences, and transforming these conditional assumptions into explicit cause-effect models. And these assumptions about the feature risk relations are then stepwisely expressed, and therefore can also be better verified and validated than is the case for trajectory-based TIA approaches. And the consequence is that using these low-risk indicators, this relieves us from having to argue the whole situation space, because we are looking for single features that lower risk. So, but we still kind of having as a baseline worst-case assumptions. And if we detect that one worst-case assumption is not true in the current situation, then we can relax to a slight extent behavior. But other approaches actually, they try to, in every situation, judge the risk correctly. And this actually means that the verification and validation for the whole situation space in complex contexts is hardly possible. So how does my research go on? So we will now in the summer plan the second round of data collection on the Kaiserslautern campus, because now finally students are back on campus, and we can then hopefully see crowded scenes and evaluate this approach. And therefore I would like to thanks a lot. And if you got curious, for instance, also about how we now build Bayesian networks out of this qualitative risk model, I'm inviting you to reach out to me via mail or connect also via LinkedIn. Thanks a lot.
All right, thank you, Jan, sorry. And Q&A session is open. Since we are a little bit over the time, I would, no, not your fault, don't worry. I would ask the question we just got in the chat, and then I would directly go to our next presenter today. So the question is, as I understood, this risk assessment model is addressing mostly the dynamic parameters associated to the context changes. Is this model also capable to address the dynamic change in parameters associated to the system as well?
In principle, yes. But this is like not the subject of my studies. So of course, if we are kind of dynamicizing the part from the, let's say, hazards and the effects the hazards have on towards the accident, so to say, and trying to capture in the models the variability of those, it is would be only consequential to do the same thing like addressing whether a hazard is actually likely based on certain properties that we have in our system. So kind of measuring, for instance, how well can I at the moment perceive certain parameters. Yeah? So their variability with respect to, for instance, the presence of triggering conditions for your perception stack can be similarly used in order to capture this variability. So in the end, what I would, on a large scale assume is that we have a big model that not only contains the risk part, but also kind of is extended towards the situation, so that we have the complete causal chain from events in our system, having events in our environment, and kind of relating them to a final risk assessment. And that would be then in fact not a risk assessment in the context of, for instance, like the ISO 26262 deals with it, but it would be a residual risk assessment, because events in your system that kind of determine the capabilities of your system to control a particular situation, they are basically kind of risk reduction capabilities that you usually have. So kind of short answer is yes, this is possible, and we are also researching in that direction and have a different approach at Fraunhofer, which is dealing exactly with the stuff that you have asked for. So, but my approach is only kind of looking at the environmental assumptions, but the same can be executed within your system.